All right, let's go through this rational function review sheet. So, two problems on here. They cover almost all of our topics. And so for this first rational function, we just want to break it down, get all the parts figured out, kind of get a rough idea of what the graph looks like. So since it is a rational function, the top's a polynomial, the bottom's a polynomial. So we can use all those polynomial tools like the rational root theorem, Descartes' rule of signs, synthetic division, all this and that. So let's just pretend, I did all that, and I've kind of got my rational roots straightened out, and so I'm going to start testing them. So I'll show a little bit of the synthetic division. So some divine inspiration. I'm going to try testing -3 as a root. And so let's see here, -5, 15, 3, -9. That's going to give me -15. This gives me +45. And lo and behold, that works. I got a 0 there. So that's a factor. If -3 is a root, x plus 3 is a factor. And then I could test, how about +5? And starting to look pretty good here. And hey, that works. And so x minus 5 is a factor. And then that last bit is x squared plus 3. So again, remember, at this point, that's a quadratic. And if you look at that quadratic, that's an irreducible quadratic, so we can't factor that anymore. And for the sake of time, I'm not going to do the bottom one, but the bottom one does factor into x minus 4 and x plus 3 squared. So now that it's factored, I should try to cancel. And those cancel. So if I get sort of a reduced form of this rational function, it's x minus 5 times x squared plus 3 over x minus 4 x plus 3. Alright, now the Y-intercept, that's pretty easy. You just plug in 0, and if I plug in 0, that's the only thing left, so -45 over -36, which reduces down to 5/4. Okay. X-intercepts, those will be the zeros from the numerator. And so let's see here. X equals 5 is a factor in the numerator. All right. Now, since that x plus 3 canceled out, that's actually not a 0. So we're safe there. All right. Vertical asymptotes. Remember, vertical asymptotes come from the factors in the numerator, and so x equals 4 and -3. Now we did get 1 power of the x plus 3 factor to cancel, but we didn't get the whole thing to cancel, so that is still a factor, and therefore that is still a vertical asymptote. Remember, if it completely canceled, that would be a hole in the function, but that factor did not completely cancel. All right, horizontal or oblique asymptotes. Now this is a improper rational function, so the degree on the top is larger than the degree on the bottom. You could do long division and get the asymptote. It's going to be a slant asymptote. The easier way to do that is you take whatever the largest power is in the bottom and divide everything on top by that. And you bring the coefficient with it. There's only a coefficient of 1 there anyways. And that reduces to what? X minus 2 and then minus 12 over x. Well, the rest of these are all over x, x squared, etc. So those, as we get large, go to 0. So what's left? X minus 2. So that's actually your oblique asymptote. So that's the fastest way to do that. But there are other methods, but I think that's the simplest. So now with all this, I can get a nice little sketch here. So first of all, I'm going to draw my asymptotes. I'll draw those in red. So red dashed lines here. So there's my oblique asymptote, vertical asymptote of 1, 2, 3, 4, and -3. And then end behavior, if I just kind of look at the signs of the original function, I can get a good idea of the end behavior. And oh, also I do have that x-intercept of, isn't it 5? So this is going to look like that. This one is down here. And this is going to go through 5/4. So this looks something roughly like this. Now this isn't perfectly correct. But the point is, using these tools, I can break it down and have a really good idea what this thing roughly looks like. So there you go. So that's it for that. Let's go to the second problem. This one's a little easier. So on this one, we got an application. This is a rational function. It predicts the deer population in a federal game reserve, and so at time t. So they aren't very specific though if t is months, years, or, well, it does say in years, but years from when we don't know. But we'll just kind of roll with it. So here we're just literally plugging in values for t. So if I plug in 15, I get 325. If you work that out. Plug in 70, you get 600. And if you plug in 100, you get 648. So just real simple substitution and working it out. What's your horizontal asymptote? Well, your degree and your top and your bottom is the same, so your horizontal asymptote is those coefficients divided, which is 800. And so what's this graph look like? Well, roughly speaking, oh, by the way, is there a horizontal or vertical asymptote? Well, vertical asymptotes are when the denominator is equal to 0. So if you solve that real quick, you're going to get t equals -25. So at -25, there's a vertical asymptote. At 800, there is a horizontal asymptote. And if you plug in 0, I believe you get, well, that'd be 800 over 20, so 40. So the graph looks something like this. All right. And then there's some stuff on the left, but I actually don't really care about that. And according to the model, what is the largest possible deer population? Well, the largest possible population would be that horizontal asymptote of 800. And then the last thing is just interpreting some things about this model. So write a paragraph that explains parts of the graph in terms of the situation. What do you know about the population? Are all parts of the graph valid for the model. Why or why not? Well, first of all, having t less than 0 does not make sense. Okay. Sometimes it can, because that can be just going backwards in time from your starting measurement. But I think in this case that doesn't really make sense. So that also tells us, by the way, that if those values don't make sense, that asymptote, vertical asymptote of negative 25 is irrelevant because that's a negative value. Okay. So what we're really saying is this graph, really, we only care about this chunk here. Okay. What else? Well, hey, when t was 0, right, the population, and did they use, I guess they used p of t. So p of 0 was, we said, 40. So this might imply they initially brought in 40 deer to start the population. Or maybe just when they formed the game reserve, there were just 40 already there or something. We don't really know for sure. But it's worth noting that there was some sort of starting value of 40. And then, of course, we already kind of mentioned this, but the max population is 800. Which fancy talk, we call that, in models like this, we call that the carrying capacity. So you might see that. That's a term used in biology a lot of times. So like in this environmental setting of this game reserve, the carrying capacity maxes out at 800. So, all right. So there you go. So 2 quick examples. I hope that's helpful, and kind of covers most of our content right there.